to that. And the first talk is efficient defenses against adversarial examples for deep neural networks. And the talk will be given by Valentina Zantedeschi and Irina Nicolae.
Thank you for the introduction. I will follow up on that by saying that Valentina is a third-year PhD student doing her research in machine learning at the University of Jean Monnet in Saint-Étienne. This summer, she did her internship with us in IBM Research in Dublin, and now we will present the project that we did together. So first of all, I think what you are most used to see in your field is how machine learning can be applied to solve different security tasks. And this has proven some success on some tasks and has created some controversies on others because maybe people were expecting great performance, which was not met. But in this talk, we'll be doing things the other way around. That is, we will be speaking about some security problems of machine learning. So first of all, some generalities. Just to set the problem, in machine learning, what we are trying to obtain are prediction models. These models are based on data, and they are obtained through a process of training, which is basically you provide to your model past data, consider in this case images, and with the expected output that you would like your prediction model to offer. And based on this training process, what you get in the end is a prediction model, which is able to provide, hopefully, the correct answer whenever you give it new data. Now, it has been found out in the recent years that machine learning algorithms in general have a fundamental problem. That is, once you've overcome the training step and you are using the model in practice, what happens is that an attacker can use some noisy input to make your model fail in practice. So consider this example. You have the picture of a panda, which is classified correctly with a high degree of confidence, 84%. Now, look at the image in the right. I would say that you cannot say that this is not exactly the same image as the original one, but this one will be misclassified as a monkey with, again, pretty high degree of confidence. Now, what changed between the two of them is the fact that this noise has been added to the image. Again, you cannot see this, but it will completely make the model fail, and in some cases, we go from almost close to 100% correct responses from the prediction model almost close to 0%. Now, what I would like for you to notice is that this noise that is added in the middle in order to make models fail is not random noise. Prediction models are generally pretty robust to random noise, but this noise here has been crafted especially to make the model fail. Now, why is this important? There are many types of applications that are currently in the process of being developed and that will be used in the following years. So if you consider self-driving cars, here we have a task of image segmentation where we would like to recognize to some extent to which class the pixels in an image are part of. And here you have the camera that is on top of a car. Again, you cannot pretty much tell the difference between the two images, but the system, when adding the noise, will fail to recognize the pedestrians. Of course, I do not have to explain what are the implications of a car not slowing down when pedestrians are involved. In the same way, self-driving cars can have the problem of not recognizing correctly road signs. So again, if the car doesn't stop where a stop sign is involved, there's some liability there. Now, another example, and this was published recently in CCS, they have built an end-to-end system for fooling all these personal assistants with some commands that are completely inaudible to humans. And again, this works pretty well, and they manage to do the assistant do whatever they want.
in order to understand why these machine learning models are affected by these vulnerabilities, we're going to need to go into the details of the structure and how the machine learning models work. We are going to focus on deep learning models that are just a subset of machine learning models. They're pretty known because of their performances, for instance, in the image recognition task. But also because of their complexity, they're probably most vulnerable to adversarial attacks. So let's first demystify their magical powers. Classical neural networks consist of neurons interconnected to each other and grouped by layers. So each neuron represents a function of the previous values coming from the previous neurons of the previous layer. Okay, so at the training step, what we actually learn is all the weights of these arrows that are connecting the neurons of a layer to the neurons of the next one. Also, all these values, the values are coming out from a neuron are passed through an activation function in order to add some nonlinearities, etc. So what we learn at training is how to combine all the internal functions in order to get the expected output from the given input. At prediction phase, what happens is that we present this, for instance, this image to the network, and the values are propagated from the input layer here through the network using the weights that we just learned in the previous phase, and we'll get an output here. Here, the neuron corresponding to, each neuron here corresponds to a class, and we retain as the prediction class, the predicted class, the neuron with the highest score. In this case, the giant panda. So what happens when we present an adversarial image, like in this case, to the network? Here we can see that there is no important difference between this image and the original one. So we are expecting the network, the model, to react the same way, to have the same prediction. But in this case, we have a monkey prediction. This is because even if the perturbation in the input layer is pretty small, it's not detectable visually, the perturbation at the end in the final layer is much bigger. This is because this difference is amplified through the network because of the discrimination of internal functions that I told you about before. So as Irina said before, not any perturbation in the input layer will result in a big perturbation in the output layer. We need to craft this perturbation in a particular way. Let's see why we need that. We can't just apply any distortion to the image in order to have a possible attack. We just choose an oversimplified illustration. We are working in a 2D space in which we represented the data distribution of two possible classes, the yellow and the orange one. So the true distribution of the data corresponds to these areas colored by the yellow and the orange. The crosses correspond to the images that we use for training. And the red line that we see here is a possible decision boundary that we have learned during the training phase. So we can see, so this decision boundary means that whatever is above that line will be predicted as the yellow class for the model, and whatever is below it will be predicted as the orange class. So as you can see here, there is a discrepancy between what is learned, what is predicted by the model, and the true distribution of the data. And this region here is where we have all our troubles. As a matter of fact, the adversarial examples occur in this area, and a possible attacker would try to modify one of these the crosses here in order to make them grow towards and across the prediction boundary, so that the model will be fooled on that example. All these examples here will be predicted as yellow class, but they are actually from the orange class. But so what an attacker will try to do is to apply the smallest perturbation in order to make these, in order to find these regions and also to make the adversarial not detectable visually in the case of the images, or also statistically. So this is why we couldn't just apply any random transformation, for instance, to this point. Because if you take any random transformation, first, we are not sure that the resulting image will lie in this region of the space. Maybe it would still be inside on the right side of the decision boundary. And also, we will not be sure to have the the smallest perturbation. And so will result with detectable adversarial examples. The problem at the end boils down to find an x prime, the adversarial example, that is pretty close to the original one, x, but that is able to fool the model to have a different output at the prediction. In the literature, there are different attacks, different approximations of this original problem. The first two that you can see here in the table are fixed budget attacks. They are the fastest, and they are pretty effective. The second one just differs from the first one because before applying the first method, we just apply small perturbation in a random direction around the inputs. And it has been shown to be stronger than the first attack. The last three attacks that we see here are stronger because they allow to find smaller perturbations of the inputs. So they are much more difficult to detect. But also, they're, of course, more computationally expensive. But let's see how we could defend from these attacks. What we'd like to do is, okay, if the problem is that we have these kind of regions in the input space that are underrepresented, why not just learn our model using a bigger data set, using a data set that will be the sum of the original examples and the adversarial examples crafted using the learned model. So the adversarial, this defense procedure called adversarial training, consists in training first a first model that we correspond to this, to the red line we saw before, using the original data set, craft some adversarial examples using that model, and then retrain the model on an augmented data set. So at the end, we'll try to correct the decision boundary, have a better one. But of course, this kind of defenses cannot work in practice every time, because we will always have new regions that are underrepresented by the training set. Maybe we cannot see it here in a 2D illustration, but we usually have to deal with bigger spaces with much more dimensions. If you think of any picture who has much more pixels than 2. Other defenses, so the first two defenses that I just described, are based on this principle: train the model, craft adversarials, retrain the model on a bigger data set. But then there are other defenses that consist in pre-processing for instance, the inputs that are presented to the model before training and also before every prediction phase. For instance, by squeezing the input domain or applying some transformation to the pictures. And also we can pre-process the outputs, the expected outputs that we use for training the model. Now that we have the entire background and we see the state of the art for the attacks and for the defenses, I can talk about our methods that we propose to make the model more robust to this kind of attack. So we tackled two different problems. The problem that we just saw, that we cannot really discover all the adversarial directions in the space, in the input space, and also this cumulative effect that that it happens in the neural networks. So our first contribution is to say, instead of learning our model on the original training set, why not try to learn it with an augmented data set that will contain also some noisy images. Okay? What we do is to draw some random perturbations around an original point following a Gaussian distribution. So because we use the Gaussian distribution, we are most likely to have to draw points around the original point, and as we go farther from the center of the distribution, we will have less and less points drawn. In this way, we are able to discover the neighborhoods around the points, and somehow smooth the decisions of the model. The second contribution consists in try to control these cumulative effects in the neural networks, because what we use at the end, classically at the end of each neuron, is this activation function that will return a 0 value if the value at the input of the neuron is negative, and we return the exact same value if the value is positive. But if you want to control the amount of perturbation that is accumulated through the network, we can simply bound the maximal value that a neuron can return, for instance, by this constant t. So let's compare our contributions to the state-of-the-art defenses. First of all, by considering the overhead that is added to the training and prediction phase. So we can say that our model, our contribution don't have much overhead at training, because we need to train the model only once, unlike for adversarial training where we need to train the model twice. And also, drawing points following the Gaussian distribution is much cheaper than crafting adversarial attacks. Also, we don't need to propose the input, we don't need to propose the output. And at the prediction, we don't need to propose the input, we just apply the original examples, and we don't have any loss in performances. Also, our contributors are agnostic to the type of attack. Okay, let's see empirically how our contribution perform. We tried 2 different data sets that are classically known for the machine learning community. MNIST dataset that is constituted of images of digits, handwritten digits. The task will be to recognize the digit in the image. And also a dataset of RGB images, for which the task will be to recognize one of the 10 objects that are in the picture. What we train are convolution neural networks that are classically used for this kind of task, for image recognition tasks. We consider 2 different settings, the black box one and the white box one. For the black box one, the attacker will have access only to the inputs and the outputs used for training the model. But for the white box one, we'll have much stronger attacks because the attacker will have access also to the kind of architecture that is used for prediction and to the exact values of the parameters learned during the training. So we'll have access to all the information as possible. The steps will consist in train the model with the different defenses, generate attacks against those models with these 2 different settings, and we'll then compare the performances of the different models defended by the different defenses. First of all, we want to try to see if the resulting amount of perturbation that is needed to add to an image has been increased. As a matter of fact, so what we used is the 10 first images of the dataset that are in this green box here. We attack the model without the defenses and with our defenses. and with 3 different attacks. So the code on the left here would be the examples that can fool a model without defenses. And the column on the right will be the examples, the minimal perturbation will be added to the example, the original one, in order to fool the model trained with our defenses. So we can see that at the end, what we obtain when we attack our model with our defenses is something that is much more different from the original examples, and it's also much more detectable visually and statistically. So in this sense, we can say that our defenses are better than no defenses. Also, we evaluated the accuracy of the model, meaning the number of times the model had the right prediction presented with the examples. We evaluate the accuracy with respect to this epsilon that corresponds to the budget of the 2 attacks here. So the budget will mean that if you have 0 here, no perturbation is added to the pixels of the picture. And going towards 1, epsilon equal 1 will correspond to a switched value for that pixel. So the maximal modification that we can apply to a pixel. Our defenses here are represented by these 2 lines with CNN plus GDA, Gaussian data augmentation with ReLU. And we can see that using our defenses, the model is much more robust for these 2 attacks. And this is for the dataset CIFAR 10. For the black box setting, we'll have also better accuracy than the state of the art.
I'll just try to do a short demo, and I will then comment on the results. So we have a web interface where you could upload photos. And I will explain this right away. So as much as we would like to show you how to train a model or how to defend it, those are procedures that take a huge amount of time. What indeed we can show you, on the other hand, is how to craft an adversarial attack, because this is much faster, so it was in the order of a second. So what I did here is to choose a machine learning model. It's a standard model you can find on the internet. Upload an image and then chose here the size of the budget that we give to the attack as a perturbation. So what we get in the end is this bird, which is correctly classified. I can tell you it's correctly classified. It's a magpie with 91%. And by applying the noise, which in this case you can see as I put a pretty high budget on it, it gets classified as a jigsaw puzzle. The noise that was applied in between is this, and well, you can see just a bit here the shape of the bird in the noise that was applied. Now, this was the FGSM attack, which is one of the fastest one, but you saw anyway that it took a while to get the response. But also what you can see maybe is that the change is not too subtle. You kind of can see a background model here. And what we can also take a look at is what the classification model is focusing on when making the decision. So when making the correct decision, this is the area that interests the model the most. And well, when going for the jigsaw puzzle, it's more this other area. So in conclusion, we have designed a defense method that is very easy to apply. You don't need to be a machine learning expert. The functions that we have used are available in any machine learning library. Our defense has overall better performance than other defense methods and does not add almost any overhead for training and no overhead at all for prediction. I think more the takeaway message for you is that maybe machine learning is not ready at this stage to being applied to major real-world applications without the proper security added on top, especially when important decisions, say national security or something like that, are based on the algorithm. Now the demo I have shown you and the experiments were done with our in-house attacks and defenses library, which is soon to be open sourced. And if you're interested in more details about the paper, you have the link over there. So thank you, and if you have any questions, we're ready to take them now.
Thank you. Questions? Ah, sorry.
So you focus on upgrading the samples or changing the samples. Are there any experiment done with changing the model itself, complexifying it in order to make it more robust to this kind of perturbation?
So the problem is that making the model more complex will just increase probably the problem. We won't solve it. We tried different architecture. It has been shown that not only CNN, but also ResNet and other pretty old deep learning architecture are sensitive to this kind of attacks. So what we really need to study is how we can prevent, maybe in the small units, as we did, or in the training or some other, or for the pre-processing, how we can erase the perturbations or make the model don't account for those perturbations.
Also, this is known to be not a specific problem of deep learning. This is true for all prediction models, and this happens pretty often when the model internally uses a high-dimensional representation space. Now, the high-dimensional space, it's what gives the model its power. So if you have 10,000 different categories of objects, your model is able to recognize them correctly because of those high dimensions, in part because of those high dimensions, but it's also what creates the problem of adversarial examples.
Hello, can you go to the slide number 30? Yeah. Can you explain what happened with number 2 and number 0? You see on the third column, number 2, it has no significant changes in your protected. And in the fifth column, the 0 is exactly the same. It falls out of the line completely.
It means that a perturbation that is not visually detectable was enough to fool the model.
Yeah, I know. But
oh, sorry.
you shown this sign, you know, the road sign, the stop. There was a slide with adversarial image and a normal one. So does it mean that your algorithm will not work on some letters, for example? And you cannot protect some road signs with this algorithm just because you cannot?
Yeah, I would say that so many machine learning is probabilistic, right?
Yeah, I know.
You are not guaranteed to get the correct response, even if you're not in the case of an attack. So what you say is true, even when the model is protected, even if the defense works well, it's with a probability of 1 minus delta, where delta, we hope, is a very small value. So you are right, there will be inputs for which, even with the defense, the model would not be protected.
So probably someone can craft a specific attack for your algorithm, yeah?
Yes. Well, you can always craft a stronger attack.
That's a good challenge.
Other questions? I have one. You have some figures based on tests you did on datasets. I was wondering, because of the drawings you did on the two different types, you know, with this yellow dataset and orange dataset, if there is a way to some way compute some kind of distance of value or error that is remaining with your method, or?
With our method, it's not possible. Actually, it's not possible anyhow, because it has been shown that as we increase the number of dimensions of the input space, the distances lose their significance. So they don't mean anything anymore. So it's a big problem.
So the only way to get some values is by doing tests?
Sorry.
By doing the tests on datasets?
Oh, yes, yeah.
Okay. Thank you again, and we'll go to the next talk.